I'm going to assume the biggest problem for this is that people do not understand how to solve it. So the very thing you need to realize is that work is equal to the change in kinetic energy. Well, the integral of work is equal to the change of kinetic energy. In other words, the area under the curve equals the change in kinetic energy. I forgot to write the integral of work. I will explain why at the end, but that's all you really need to solve this, so I'll walk through it. So for A, first we need to know what the kinetic energy is at first. So just plug in 1/2 mv squared, plug in the m and v you're given. I got 32 joules. And then because of the work energy theorem, we know that the area under the curve will equal the change in kinetic energy. So to find the area under the curve, we just note that the scale, at least in my case, is 4. So here is just 4 times by 1 divided by 2 because it's a triangle. So it's plus 2, and then here it's minus 2 because it's under the line. It's negative, and then minus another 4. So then the KE at this point, at x equals 3 for me, would be 32 plus 2 minus 6, or 28 joules. It's just area under the curve, and just don't forget your scale. For B, it's very similar. It's asking you at what point will it reach negative 16 for my case. And if you realize, after 2, it constantly decreases by 4 joules for every meter, because the area under the curve is 1 times 4. So then you just need to figure out how many, times it needs to be subtracted by 4 to reach 16. So I decided to use x at x equals 3, the joules is 28 from the last question to solve this. So the change in energy from 16 to negative 28 is negative 12. So it would take 3 more meters for it to lose 12 joules of work. And well, 3 meters more than 3 is 6, so that's B. And then for C, if you notice, after 1, the work is only getting smaller because the area under the curve is negative. So at 1 is the highest it will ever be, because then the work will eventually reach negative and it'll go on to negative infinity. So at 1, it's the highest it'll ever be. And we already figured out what this area is. It's just 1/2. It's just 1/2 times 4 times 1, which is 2. So take your initial, 32 plus 2, you get 34 joules. And that's all you need to know. But if you want to know why is the area under the curve equal to KE, well, conceptually, kinetic energy and work are the same thing. Kinetic energy is kind of like the momentum of it almost, while work can you either cause or stop it. But mathematically, they're directly related to each other. So how I'm going to prove it. Work is force times distance. We all know that. And the area under the curve for any equation is the integral. So when you integrate force times distance, you will get 1/2 mv squared. How? Well, we can set up the integral like this. From indefinite integral from distance over to 0 to distance times by f, or f. Why? Well, distance is just distance traveled, and on your boundaries, you always use the distance in that. And we don't have a given starting point, so we just put 0. So that's how we get here. But then remember that force can be written as mass times acceleration. Mass is just a constant, so if you remember from calculus, any constant can just be pulled out when you integrate. So then your mass out here. And then remember that we need like a dx. We need a change for each bit. But acceleration can be written as velocity over time, change in velocity over time. See, velocity is change of distance over time, acceleration changes velocity over time, joule is change of acceleration over time, blah, 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 blah. So you can rewrite acceleration as velocity over time. So this /t is basically like your dx. When you integrate it, you can ignore it. So then treat v like an x. The integral of x is just 1/2 x squared. We should know that. So if you integrate this, you get mass, because you pulled it out, 1/2 v squared. And then notice that if we were to rewrite this, we could just write it as 1/2 mv squared. This is Ke. And since we just integrated force times distance, or work, we know the area under the curve is equal to this, which is equal to kinetic energy. And that's the proof for the work energy theorem. You don't have to know that though. You can just remember